believe the number is still soaring up. So hello, welcome to ESIC's seminar series. I'm John, the seminar coordinator. I will be moderating the seminar with our communication specialist, Kathy Medley. Our Dr. Hugo Burberry also joined us, and Hugo is Deputy Director of the Cooperative Institute for Satellite Earth System Studies here in ESIC. And Hugo will be introducing the speaker. And the seminar is being recorded. We will publish the recording on our YouTube channel. It usually takes a week or so. So please feel free to check it out. And after the presentation, we'll have the Q&A session. Please feel free to bring up any questions you have. You can unmute yourself, or you can chat us your questions, and we will read it out. Before the speaker gets started, we'll have our Deputy Director of the CSS, Hugo Burberry, to introduce the speaker. So Hugo, please go ahead.
Oh, good afternoon. It is my pleasure today to introduce Steve Goodman as the speaker. Steve has a long history of work at NOAA and NASA, and at present he chairs the World Meteorological Organization Global Climate Observing System, GCOS, task team on lightning. But he was for over 40 years working with NOAA and NASA. And in that role, he was the chief scientist for NOAA, the GOES-R program. He also served as a member of NOAA and NASA Space-Based GEO and LEO Lightning Mapper. Steve retired in 2017 and has continued working as hard as always. He's now a senior program advisor for NOAA and NASA. And in the past, before retiring, he was at the NOAA Council of Fellows and did a number of activities, all related to the Lightning Mapper and the GOES-R information. So he has over 80 papers that are peer-reviewed, books, book chapters, but I think that the overall body of his contributions is much more than the papers themselves, with all his guidance for all these programs. And Steve is an affiliate member of CSS, which I am quite happy that he is. So with that, I will give you the floor, Steve, for you to start.
All right, thank you, Hugo. So you can read the title slide. What I'm going to talk about is a project with the WMO Global Climate Observing System that began in 2016. There's an atmospheric observations panel for climate, and they recommended that this task team be formed to explore how and whether there should be lightning declared an essential climate variable, which did happen. It's number 54 on their list, and I'll show you that later. We had our kickoff meeting actually in College Park at the ESIC building in February of 2017. We did a report, and now the GCOS has just come out with their next 5-year implementation plan. I'll talk a little bit about what we're doing for lightning with that. And then on the list here, you can see my task team co-members from around the world. And then Katerina Tassone and Tim Oakley are our sponsors at WMO and GCOS for this activity. Well, let's see, advance. I'm not, oh, okay. So why lightning for climate? Lightning is perhaps the most common natural hazard on Earth, with hundreds of millions of flashes per year worldwide, responsible for fire ignition. It's a public safety hazard, and scientifically it's interesting as a natural source of NOx. Nitrous oxide is also an essential climate variable. Let's say I gotta minimize the screen here. Yeah. So one of our initial tasks is to come up with what would the climate data record look like for lightning. And right now we've gone out to the providers of the data to get details on the metadata, things such as measurement accuracy, the detection efficiency, which is a key parameter for lightning networks, either space-based or ground-based. False alarms, things we say are lightning, but they're not, they're noise of some sort. And then harmonizing these data sets and produce a data set for the scientific community is our end game by basically a year from now, next April, 2024. We recognize that no single observing system is 100% detection effective for lightning. Signals are either weak, below threshold, or don't cover certain parts of the Earth. And then I want to close with some grand challenge science questions and also some trends in climate modeling where people are looking at lightning. And the key question is, how is lightning related to the other climate variables? And how is it related to severe storms, extreme weather, fires, aerosols, clouds, precipitation? And I'll show you some examples of trends in lightning suggestive of a response to a warming Arctic. I don't know how to get rid of this top panel here. Hopefully it'll go away. There we go. So the value proposition for lightning for climate, an essential climate variable is a physical, chemical, or biological variable or linked variables that critically contribute to characterizing the Earth's climate. These ECV data sets provide the empirical evidence needed to understand and predict the evolution of climate, guiding mitigation and adaptation measures, assess risks, and I'll show you an example of risk assessment in the energy industry, and enable attribution of climate events to underlying causes, and I'll speak to that as well, and underpin climate services. And they're required to support the work of the UN framework, the Convention on Climate Change, and the Intergovernmental Panel on Climate Change. And here on the image is a couple of the reports that we've been involved in writing. So here are your essential climate variables, atmosphere, land, and ocean, and you'll see lightning listed here under upper air. I don't know why we aren't listed under clouds, but we are on the list. And so one of the complex questions is the interrelationship between these essential climate variables. So how's lightning related to temperature change, water vapor changes? How's it related to aerosols, greenhouse gases, clouds, ozone? I mentioned nitrous oxides and so forth. So weather has lots of impacts on society that involve lightning. For example, lightnings in hurricanes, tornadic storms, flooding storms. In particular, lightning is useful in the Intermountain West, where radars are beam blocked and don't see the low-level precipitation fields as well. Even blizzards, you probably heard of thunder snow, so lightning does occur in these winter storms. Typically, they have high liquid water content. Lightning's a danger all of its own. Lightning ignites forest fires. Lightning's observed with volcanic eruptions and so forth. So the way I think we got going in 2016 was there's been some studies from the Tropical Rainfall Measuring Mission in this paper by Ed Zipser et al. And where are the most intense thunderstorms on Earth, which I'm showing in these 4 panels. The TRIM microwave imager at 37 gigahertz at the top, 85 gigahertz, which is responding to ice scattering in the clouds in the second bar. The precipitation radar on TRIM, which can measure the height of the reflectivity cores. Here's the height of the 40 dBz echo. And then at the bottom is our lightning imaging sensor that flew on TRIM, showing you flash rate. And while there are very much similarities in these fields, there are also differences. If you look at the lightning flash rate, if you look at the central Great Plains of the US on the left, and then the La Plata Basin in Argentina, where Hugo's from on the bottom left, you'll see these black marks, which are the highest values. So we have very small number of what's called precipitation features, but these are where we have the most intense lightning. They're coming from mesoscale convective systems. And you can see the number of storms observed as I have here on the right. And these La Plata Basin storms are the most intense storms that we observe, excuse me, on Earth, with 1,000 discharges per minute that go on for many hours. Here's a slide put together by Scott Roblaski, who's the NESDIS lightning lead, and how forecasters are using the lightning on the geostationary lightning mapper on GOES-R series to observe lightning in severe storms. Top you see a derecho, bottom left you see eyewall hurricane lightning, and then you see fires started by lightning. And National Weather Service is using the lightning data for impact-based decision services, aiding in severe storm and tornado warnings, excuse me, identifying the location of possible wildfires. Lightning data at mesoscale models has been assimilated into data sparse areas like off the coast to fill voids not covered by radar data, precipitation data to be assimilated. And tropical cyclones, you can see, and even interannual and decadal variability. And lightning mapper value assessment, which we did to prepare for the next generation GOES series called GeoXO, Geostationary and Extended Observations, which just got a new start at the end of last year. We'll also have a lightning mapper on board on the east and west satellites like we do now on the GOES-R. And one of the topics in our value assessment is lightning and climate change. Here's the Tonga volcano, which I'm sure everyone's aware of. Here's the eruption of the cloud on 15 January 22. This is the GOES-17 looking out to the west, Indonesia. The visible image, it was a very rapidly explosive explosion, so strong updrafts, and we know lightning is occurring with some volcanoes. Here's a plot from Vaisalov from their GLD 360 data showing lightning every 10 minutes from this explosion into about a 3-day period. And the underwater eruption triggered the main event. 400,000 lightning strikes were recorded in 6 hours that evening. Now with the satellite, we're observing the light getting through the cloud at cloud top, and that ash is very dark and thick. And so not much of the lightning was actually observed by our satellite instrument. So these ground-based radio frequency measurements are quite excellent and complementary to the satellite data for creating a comprehensive climate data set. And you see here the last statement, their network detected 25,000 lightning strikes in a 5-minute period and almost 600,000 lightning strikes over the 3 days from that really intense eruption. This is a WMO slide. So what I'm showing you here is what we call the georing and the operational satellites. And I'm pointing out here in the global observing system where we have lightning mappers. So G18 and G16 for GOES shown here in the left, 137 west, 75 west. Europe, the EUMETSAT launched the Mediasat 3rd generation I-1 satellite with a lightning imager. That's at 0 degrees. And then China back in December of 2017 launched their Fenyang 4A geostationary satellite, and that has a lightning mapping imager. And so these geostationary lightning mappers, which can nearly continuously observing lightning, are helping form what we call the georing of lightning observation. In the georing, the satellites in orbit are on the top line across here, and GOES-R, there's the lightning mapper, has an imager and a lightning mapper, and then planned satellites, the GeoXO I-1, if we have an imager, we have a lightning mapper, we have ocean color, and then we're going to have a central satellite for the first time with an IR sounder and atmosphere composition instrument. Excuse me. I also show NASA because NASA's flown research lightning instruments. And shown here is a follow-on to the TRIM lightning imager, which is on the ISS, called the Lightning Imaging Sensor ISS, which was launched in February 2017 and is underflying the GLMs we have in geostationary orbit provides basically a reference radiometer where we see at higher resolution, about 4.5 kilometer pixels, lightning as the space station flies overhead. We observe an individual cloud for only about 90 seconds compared to continuously throughout the diurnal cycle from geostationary orbit, but it is providing very good data that extends the climatological record. And this is from NASA's Joint Agency Satellite Division, where NOAA's JPSS, low Earth orbiter, and the geostationary satellite data reside at NASA headquarters, and they're helping us in a joint program develop the instruments for the next generation called GeoXO. I is for imager, which has the lightning mapper and the 18-channel multispectral imager, and then the S satellite will have, as I said, the atmospheric composition and the infrared sounder. Here's a news release regarding the GeoXO program, and you can see the different measurements, imagery, lightning mapping, infrared sounding, ocean color, atmospheric composition. And you can go to that website and read the press release from NOAA. So here we're back talking about GCOS. The implementation plan just got finalized as a 5 to 6 year plan. We have 2 actions in there for lightning. One is to reprocess our low Earth orbit NASA data and our geostationary GLM data. And then also on the right here, I show some of the, one of the pages from our Bulletin of the AMS August 22 issue, where for the first time we were given 700 words to talk about lightning and climate. And we show a time series of lightning back to 1997 when the TRIM satellite launched, with a few-year gap till the space station, and then the spatial distribution above that. I'll say more about that at the end of the talk. So in trying to reconcile the ground-based radio frequency measurements of lightning and the space-based optical measurements, shown at the right, you see the puddle of light we observe at the top of a cloud. If you look at the development and evolution of the life cycle of a storm, what you see is here, generally when a storm begins, it's mostly vertical, it's not too wide. You end up with a vertical dipole of charge, a positive charge on the small particles aloft, and then negative charge and the grapple that's in the main part of the storm. And so you start with in-cloud lightning, then you have cloud-to-ground lightning. Then the storms may grow upscale, become multicellular. The lightning may become more horizontal. It may go out into the anvil as shown here in panel E, and then continue going to ground and have in-cloud and cloud-to-ground lightning. So we look at such lightning from space, looking down on cloud top. What we see are individual pixels resolving the lightning discharge channel, and they're plotted here with the first detection indicated as T0 times 0 is the first event, and we group these together in space and time to make a lightning flash. And I've overlaid the lightning pixels on top of one of these ground-based lightning mapping systems to show the channel structure beneath the cloud. And then when we have our data sets, we give a latitude longitude for our flash with the mean XY, which is radiance weighted, but then we tell you also how many of these groups or strokes are in a flash, and then where the individual pixels illuminate. If we look at the ground-based radio frequency networks, they operate at different frequencies in the ELF 30 to 30 hertz band, or commonly the very low frequency band of 3 to 30 kilohertz. And we have at least 3 networks that cover lightning globally with varying capability. Medium frequency, 300 kilohertz, that would be more like our National Lightning Detection Network, which sees cloud-to-ground strikes very, very well and sees a growing fraction of the in-cloud lightning, maybe 50 to 70%. And then very high frequency networks are able to detect the lightning channels and map them out in 3 dimensions, like I showed in that previous example. The global VLF data that we want to have as part of our essential climate variable data set are from the Worldwide Lightning Location Network, Earth Networks, Global Lightning Network and the Vaisala Global Lightning Dataset 360. And some of these data sets go back to 2004, will undergo reprocessing as well as the space-based data. And we hope that will provide a very rich data set for people wanting to do research on lightning by itself, lightning and thunderstorms, and the relation to other climate variables. Here's the Vaisala GLD 360 stroke density for a 5-year period, 2016 to 2021. And you can see most of the lightning is over the land. It looks very similar to what we get from space. Here's the stroke density for 2022 alone. You can see there's a bit of a change between the 5-year average and the most recent year during this triple dip La Nina, as we call it. And then here's a comparison between the lightning density shown at the top on a 0.1 by 0.1 degree grid, which will be our central climate variable data set for all the products, and then a product called thunderstorm hours. So emulating what a forecaster might detect when they report thunder herd. If you look on the right here, you put a circle with a radius of about 15 kilometers around the data and say, okay, anything in that radius I'll assign to this grid cell, and you move from grid cell to grid cell, and that's how you create thunder hours. And during the 97-98 El Nino event, we observed with the National Lightning Network about a 200% increase in lightning hours and lightning duration, as there were many more storms that came across the southern Gulf of Mexico, across the southern branch of the jet stream through Texas into Florida. So it's a useful data set, will complement the other data sets we have. And for some of the providers, that is what they're offering up. And then here's from Earth Networks. This is their in-cloud and cloud-to-ground data. This is their version of thunder hours. You'll see some differences in these data sets because of how the different systems perform. There's a paper by Elizabeth DeGangi in 2022 in BAMS that describes how they make this product. And you'll note the Congo Basin is very rich with lots and lots of lightning. Now, with GLM in space, we can see much further than any of these individual ground-based networks. Typically, they plot where the lightning strikes the ground, but they don't give you the propagation and extent of the lightning, which we get from space. And then here's a plot from Scott Rudlowski and Michael Peterson that is the recognized WMO world record lightning flash. It traveled 768 kilometers on 29 April 2020, and it dropped 86 cloud-to-ground strikes as it propagated from Texas all the way into Southwest Alabama. And I think until we saw these kinds of flashes, of which I believe in the first couple of years of GLM 16 and 17, there were over 5 million of these. They're produced by mesoscale convective systems, and it changes your view of risk. For example, if you're outdoors and a squall line of storms has passed you by, you're not in the clear because some of these long flashes can still propagate into charge regions that trail the leading convective edge of storms. And how we can better make use of that so people understand their risk when they're outdoors is a future need that we need to address. So what are our lightning data requirements? We're looking for total lightning stroke density. We want consistent harmonized data between the space observation shown on the right from GLM 16 and 17, as well as these temporal data sets running from monthly, daily, and hourly. Right now, we expect at a minimum monthly grids to be available to users by 2024 as we're producing these. And the global product would be a nominally 10 kilometer by 10 kilometer, 0.1 by 0.1 degree. The space-based data sets would come from the previous lightning imaging sensors on TRIM and the International Space Station, NOAA's NASA's GLM data, CMA's LMI, Lightning Mapping Imager on FY4. My understanding is FY4A is what I'm showing here, but FY4C, will have an updated, improved lightning mapper. And I think planned launch for that is like 2025. So eventually we're getting to this GeoRing, and then EUMETSAT's MTG lightning imager is going through commissioning, and they're just now getting their first data, and public data should be available in November. The ground-based RF data, principally commercial data from VISL and Earth Networks. The University of Washington Woolen Network is a research network operated by Bob Holtzworth there. And then we also would like to get regional networks which do the best job of classifying in-cloud versus cloud-to-ground data. So there's interest in the lightning type. So for the metadata, we want the stroke density, both the optical flash density from space, the ground-based stroke density, global and regional networks. We still need to do a better job understanding how is the satellite event group and flash data that we get optically related to the strokes we get from radio frequency measurements. And then we want this harmonized comprehensive data set, detection efficiency, resolution, other CalDAL performance parameters, network flash type, discriminating in cloud or cloud to ground, lightning to make the data set most useful to the community. And again, noting no measurement is 100% detection efficiency effective. One of the most recent advances, Jacqueline Ringhausen, the paper references at the bottom. She, in her PhD work, has looked at trying to use attributes of the GLM data. You can see those on the right here. The group or stroke area, events, its propagation, its shape, and so forth to try and discriminate in cloud from cloud to ground data, lightning data types. And she was pretty successful. I think she had over 70% classification accuracy. We'd like to include this in our reprocessed data set so we can say something about the likelihood that a lightning observed by GLM these past 5 years is in cloud or cloud to ground. And one can also use the ground-based data in concert with the space-based data to understand that. And she developed a random forest model, and others are still looking at these types of approaches for squeezing more information out of the data. It's not just about observing or measuring lightning flash rate. There are other attributes that are important, such as the duration, the aerial extent, and the spatial extent. We're showing you a couple of hotspots for North America. We wanted to do a comparison between a paper that Rachel Albrecht, who's at the University of Sao Paulo and was previously a postdoc of mine at KICS at the University of Maryland, for the low Earth orbiting data, and where she found hotspots around the world of lightning. We want to do that for geostationary. And Katrina Wirtz developed these plots. She's a member of the GLM science team. And what I want you to notice as we went through this cursory analysis of what do these different systems show us is here's GLM from 2018 to 2021, looking at hotspots where the minimum distance between individual hotspots was set at 100 kilometers. So we didn't have all the numbers in the same location. And what I want you to notice here, 7 and 8 here in the Atlantic off the Florida coast, these are not even real. These are artifacts of the electronics of the GLM instrument. These are some of the types of things we need to remove. Cuba is a hotspot. Number 1 here is in Central America in the highlands. All right, let's compare that to a couple of the other ones. Here's GLD 360. You again see a maximum hotspot here on the western mountains of Mexico. Cuba is also a hotspot, but you see Florida ranks number 10. You got many other hotspots in the Central Great Plains. Here's Earth Networks. You can see its distribution, number 1 here in Florida, and number 3 of the top 10 here in the Northeast US. If you compare that to Vaisala and to the satellite, it's nowhere near the top 10. Well, the reason they get number 3 ranking here is because there's a high density of stations in the Northeast US. And so the closer the spacing of their network stations, the better they're able to detect the lightning, especially in cloud lightning, which is more common than the cloud to ground lightning. So there's a bias in these data sets for different reasons, and those are something we want to describe in the metadata, and the user has to understand so you don't misuse the data. And then lastly, here's the Woolen data from Washington. And you can see the hotspots are all along the coast. And it turns out that at VLF frequencies, the lightning propagates across the seawater very, very well. And so they're more sensitive to strong lightning flashes out over the ocean. And so again, one needs to understand that to understand their data. But anyway, these are the types of data sets we hope to corral and have go back in time, and just the researchers have to understand what they're working. All right, regarding some what I'll call grand challenge science questions, here's iterative variability in lightning teleconnections due to ENSO. So when we first launched the lightning imager in November 1997, right around Thanksgiving, we're able to capture the 97-98 El Nino. Here's DJF, December, January, February of 97-98, and then the next year, the La Nina event. And note the big red spot here in the Gulf of Mexico. And there was a big increase in lightning activity, thunder hours, as I said, thunder days, and so forth. We added up 16 cyclogenesis events due to the southern branch of the jet stream coming along the south coast of the US. And again, you see a big bright red spot in the north part of the South China Sea. And again, look how different it is in La Nina. So lightning is good for looking at these interannual differences, which are linked to the large scale circulation. And then on the right here, I show lightning days. Think of Thunder Day records. And I go back to 1989 with the Vaisala National Lightning Network. And you got this huge maximum in 97-98 when we had the El Nino event. And again, a big change in the lightning. So it is something worth looking at with thunder hours, thunder days, daily and monthly and so forth. So here's another example. The 2019-2020, we had COVID, and there was an observed reduction of lightning. And the question here you see in the plot from the lightning imaging sensor going back to the beginnings of TRIM, the break before ISS, and then the last 3 years, and you see the dip. And it was, a number of people suspected, oh, that might be tied to aerosols due to reduced industrial activity due to COVID. And we know aerosols are important for the development of clouds and updrafts, and even a CCN for cloud microphysics and hence lightning. But what we now know is there's also the triple dip or 3-year La Nina event that went from 2019 to just March of this year. And so a question on the table that no one's addressed is, how does the lightning activity change relate to La Nina circulations, aerosol concentration, and so forth? And I call this a grand challenge science question because it's a tough question to unravel. Another one is lightning related to a warming Arctic? So we can't see the Arctic from our space-based measurements in low Earth orbit or GEO, but here is a plot from the Worldwide Lightning Network. It has a couple stations that go up to 70 degrees latitude, excuse me, on the north slope of Alaska. Here's their lightning density, 2010 to 2014. Again, this is a very low frequency, long range system. Then you see this area of lightning activity above 80 north, 2015 to 2020. And then in our report in BAMS last year, you see even increased in 2021. And it turns out now that Bob Holtzworth has a proposal to the DOE ARM program to put 2 more stations up on the north slope of Alaska at 70 degrees latitude to hopefully get better measurements. And Sandia Laboratories, DOE, they have a number of lightning detectors on satellites in MEO orbit that cover the Arctic. And we're currently working on a project to see if that data are good enough to observe lightning over the past few decades and add that to our essential climate variable data set for the very high latitudes. So here's a plot from GLD 360. They also observed that increase of lightning in the Arctic. And you note that it's pretty flat until you get to about 80 degrees latitude, and it's the high latitudes where you're seeing this big increase. Here's 85 degrees. So the question, what's going on up there? Is it due to fires in Siberia, creating aerosols? Is it due to the diminishing ice up in the high Arctic, and so the albedo's changing? We really don't know, but we are seeing a change that is worth exploring. I mentioned risk. So as part of our user engagement in that report that Scott Radlowski led, looking at the societal benefits for lightning mapper on GOES-R and GeoXO, wind turbines are starting to proliferate with renewable resource energy, and lightning is not a friend to these very tall wind turbines. They stick up there, they create corona, and they attract lightning. And so here we went to a US Geological Survey database where they have the wind turbines, and those are in black. And here we map the lightning density from GLM 16 from 2018 through 2022 against where these wind turbines are. And you can see, depending on how the latitudinal shift may be for lightning maxima, you do have a number of these wind turbines that are in higher risk areas due to lightning. And the next slide, thank Vaisala for this as well. They've got a plot here of lightning and wind turbines due to winter storms. And here you're looking at Buffalo, New York, which gets lots of snowstorms, and snowstorms on the Great Lakes can in fact make a good amount of lightning. You see on the global map here, the US map, here's where Buffalo is. And looking at in-cloud and cloud-to-ground lightning that's observed around these wind turbines. And so if we can map lightning over large areas, not just the US, but the globe, you know, we can do modeling studies that look at the risk assessment to renewable resources such as wind turbines. And we can also look at threats to the energy grid, to the transmission lines. And a couple of folks have taken a look at that to look at risk. All right, climate change and lightning to wrap up. A couple of papers, David Romps et al. Looking at lightning strikes due to global warming, and what they do is they create a parameterization of lightning using CAPE, available potential energy, times the precipitation rate. It's not bad, but it's not perfect. It doesn't work well over the oceans. But over land here, you can see some plots. Here's lightning versus precip. There's a fair amount of scatter. You look at lightning versus CAPE shown down here. You see there's also scatter. The explained variance, or R squared, is only about 0.5 for that. They used that in 11 climate models, and they showed a 12% increase due to each degree Celsius of global warming projected over this century. So here's another plot showing CAPE on the left and precip on the right, trying to derive what lightning would look like, as I showed you just before. Here's another paper by Yang Chen. He's Lawrence Livermore, looking at future increases in Arctic lightning, this high latitude lightning, and due to fire risk, and the effect that might have on releasing permafrost carbon due to the fires, and the fires due to the trees, and the warming that would cause. He also uses, because David Romps is a co-investigator, they also use this, excuse me, CAPE precip index for lightning to make their projections. Excuse me. So looking at how is lightning related to wildfire, how does that control forest expansion, how does that affect the loss of organic soil and permafrost thawing. And DOE now has, I think they have the fastest supercomputer at Oak Ridge, and they're starting to do simulations, and they do have an interest in looking at lightning and fires. And again, this gets back to the user engagement related to the energy, excuse me, utilities, and the effect of a warming climate. But one thing I wanted to point out, I only got 2 equations in here, I apologize in advance. For those not familiar with CAPE, convective available potential energy, units are joules per kilogram. It describes the maximum amount of potential. Keep this in mind. Potential energy, which an air parcel has available for convection. Just because it's available doesn't mean it gets released. So it's measuring the virtual temperature of a air parcel here at T prime V minus the environment, integrated over height from the level of free convection to the balance temperature. And so this is what they use to get an estimate of what should lightning be like. And I wanted to just make you aware, there's another way you can do this. This is work we did under GOES risk reduction by Bill McCall in Huntsville, myself, and some others, where instead of looking at CAPE in the environment, what we find when we look at individual thunderstorms, you might have a huge chunk of the United States, for example, that's unstable. But the lightning and thunderstorms are occurring, say, where you've got a front passing through, where you have some very focused forcing. So we decided it would be more useful to come up with a physical parameterization related to updraft intensity, which you can predict from the model W, and Grapple mixing ratio, QG here. And we measure that at the minus 15 degrees sea level in the mixed phase region. So what are we saying? We're saying the flux of particles that goes through the cloud and freezes and has charge exchange is a good measure of the likelihood of low, medium, or high amounts of lightning. And we also have another parameter called F2, looking at the ice that's in the cloud, grapple, snow, and cloud ice, recognizing that while it doesn't have a big effect on the lightning flash rate, it captures the fact that we do have lightning in extended anvils. I showed you that long horizontal flash that goes into the stratiform rain area. If you only look at the leading convective line where the deepest convective cells are, you don't really capture the full effect of the charging and the resulting lightning. So we came up with this parameter F3, which combine these two. You can see max grapple flux plotted versus max flash rate, flash origin density, and you can see it's a fairly good relationship. Again, not perfect. And then here are some references from our papers in 2009 and in 2020. We looked at the sensitivities of the WRF model to this lightning forecast algorithm. And then Marion Mittermeier from the UK Met Office had used our scheme in the Met Office 4K variable model to look at predicting lightning over Lake Victoria in Africa. And so there's a few groups that have experimented with this, and as climate models start going higher and higher resolution, say from 2.5 degrees to 1 degree to 50 kilometers to 10 kilometers to even 1 kilometer, like in the DOE supercomputer, you know, these kind of schemes might make some sense to look out, maybe not for a century, but maybe, you know, out for years to look at what the effect is of the environment on lightning. So our scheme that we came up with is operational in the NOAA rapid refresh model, the HER or the RAP, as you might call it. So here's the website that you can go to see our lightning forecast, or the NOAA lightning forecast. And then here's the frontal page, and they make predictions of many, many variables. And I also captured the lightning threat 3, which is one of these many variables that they're predicting. And you can look at an hourly forecast. So I got an example from last Friday where we had some severe weather. So this is April 20th at 02 UTC. We had an outbreak of storms. And what I just want you to note here is this is surface-based CAPE, but if I look at maximum CAPE or any other version of CAPE, look at the large area that's, say, 2,000 joules per kilogram, all the way down from Mexico all the way up to Iowa. It's a very large area. Okay, now look at where the lightning is. So lightning is only in a more limited area, and that's why we're suggesting, even for the climate models, our scheme or one like it, where you focus on the cloud kinematics and microphysics, proved to be useful, because if you're using CAPE alone, you're over forecasting where you're going to have lightning. So again, this is from last Friday. This is the forecast lightning threat from the HER model. And then what was reality? So here is GOES 16 or GOES East, and I'm showing you a plot. These lights are the night lights as seen from the VEERS low Earth orbiting instrument. And then here are the clouds from the ABI, the Advanced Baseline Imager and GOES, and then lightning from the lightning imaging sensor, from the geostationary lightning mapper. And there is, interestingly, a storm with lightning that made severe weather, and I believe there were a couple of fatalities in central Oklahoma. If I go back, we don't have lightning forecast in Oklahoma, but the lightning forecast is only as good as the model. So if the model doesn't forecast anything, you're not going to get anything. And I just want to close with the new kid on the block. EUMETSAT in December launched their Meteosat third generation satellite called MTGI-1. And here's the coverage of their lightning imager. We have one telescope on GOES-R GLM, and they have 4 telescopes. Here's the lightning imager right here, 4 telescopes. This is the flexible combined imager, which is their version of an ABI. And here where the 4 telescopes have their view, and I want you to pay attention to read camera 2 area covering the Mediterranean. So here's a plot from ground-based lightning data from Bob Holsworth of what he calls super bolts, or these are the most energetic lightnings. And in the wintertime, we see these in the Sea of Japan, the Mediterranean in particular. We saw that in the optical too, from the lightning imaging sensor, very energetic lightning over the Mediterranean. The other thing they see here, not just Mediterranean, but here off the coast of Spain and France, and I showed this plot to the Europeans, and they said, you know, the ships that go through there have very dirty diesel fuel. And so they create a certain kind of CCN, and it may be the lightning is due to the ship tracks and the type of aerosols you get out of the smokestacks. Here's the field of view again of the MTG satellite compared to the GLM East and GLM West coverage. GLM East goes from the west coast of Africa to New Zealand, and you can see with camera 1, there's a fair amount of overlap with GLM, a little bit with their camera 2. And so one of the post-launch verification validation studies will be to compare GLM and their satellite lightning imager. And then I want to show you this plot, again on the topic of aerosols from Thornton et al. In 2017. What they did is they looked at PM 2.5 from aerosols. Those are particles with 2.5 micron diameter. And you see you've got these lines of and enhanced regions of PM 2.5 occurring in these shipping lanes. And then here you see where you've got enhanced rolling lightning. And it's very interesting that these PM 2.5 maxima are where you see enhancements of the lightning. So there's some certainly evidence for lightning and aerosol being linked together, and it'd be interesting to see what they see with the MTG lightning imager in space in the Mediterranean and off the west coast there of Europe. So in closing, our 5-year implementation plan, these are the activities we're doing. We have a 2-year extension ending next April, basically, to establish stewardship of these lightning data sets we use for climate studies. They may assign a liaison to the Atmosphere Observation Panel for Climate to help continue coordination with the lightning data sets. We have outreach to operators of these data sets that they would provide them on their own nickel to us, but we'll provide the stewardship. NASA headquarters has agreed to take care of and fund at the data center, holding and distributing the climate variable data sets for lightning. And then data stewardship, the global VLF operators, if I name 3 of them here, will provide the stewardship, maintain and update their product. We'll have copies of the monthly grids stored at the NASA data center. So if anything happens to these companies, you'll still be able to get those data sets. We'll have a landing page that will point to them So if you want more detailed data information, you can go to the data provider. NCEI, which is also linked very strongly with CSIS Cooperative Institute, will have the stewardship of the operational and reprocessed GLM data, not the ECV gridded version of that data set. Will be archived by NASA at the Global Hydrology Resource Center in Huntsville. And that's where the reprocessed data will reside. So in summary, lightning is a global natural hazard of great importance and interest. We're looking at exemplary data sets from satellite and ground-based networks, Thunder Hour from Earth Networks, Vizsla and GLM gridded data at 0.1 by 0.1 degrees from all these different data providers. It'll be provided in response to the GCOS 5-year implementation plan, and we'll have archival is already going to be supported. Many questions to be asked. For example, how's lightning related to other variables? Clouds, precip, composition, NOx, surface observations like temperature, severe weather, ENSO, the Madden-Julian oscillation, upper level humidity, and whatever else you can dream of. And then lightning safety awareness. So we're collaborating with the World Health Organization and the WMO Disaster Risk Reduction Natural Hazards Program on making the lightning data available. There are supposedly tens of thousands of deaths worldwide, especially in lesser developed agrarian countries due to lightning because they don't have a good place to go for shelter. So with that, I'm done. I guess I'll take questions, and thank you for inviting me to present.
Thank you. So if anyone has any questions for Dr. Goodman, this is the time to ask. You can raise your hand, or you are able to just unmute yourself and ask it. And if you don't have a microphone, go ahead and type it in the chat and I will ask the question for you. Anyone want to start us off?
I got a question, very informative talk. So about the possible CNN effect on the on promoting the lightning, I think I do see some publication studies on this topic, and given that the aerosol can either invigorate or inhibit the precipitation. So what's your thought on is it possible that the CNN or aerosol could inhibit the lightning as well?
Right, so you're referring to some of the earlier papers by Danny Rosenfeld, and he was looking at the role of aerosols if low levels in the cloud causing the rain to fall out. If the rain falls out before it gets into the mixed phase region in the freezing zone, you're not going to create precipitation, ice, and grapple, and we need that interacting with the liquid drops to do the charge exchange. And so you might see reduced lightning due to aerosol scavenging out the rain. I've seen some very detailed modeling studies where people basically conclude, boy, it sure is complicated looking at how updrafts and clouds evolve because of the role of aerosols that we really don't understand well enough. So it's a very, that's why I call it a very challenging problem to address. And I know Ken Pickering, who used to be at Maryland, used to be at Goddard, he's part of the Tempo science team, is very much interested in looking at the relationship between composition and lightning. So people did Dale Allen at Maryland as well. So I know there are people who are trying to unravel the complexity of this relationship.
Thanks.
I saw somebody with their hand up right as John was asking that question, but they lowered it. I think it was Sean Lee.
Yes, it was me.
Hi, Sean Lee, how are you?
Good. How are you, Steve? Great talk.
Good.
I was thinking, looking at slides, talking about the David Rump's paper and your parameterizations. Yeah. Have you guys applied maybe David's scheme to models and compare? How do they differ?
So, yeah, so for the WRF model, for example, David Bright, who was at the Aviation Weather Center in NOAA, he had something he called the thunder parameter, which was based primarily on CAPE. And what we noticed was that half the country would be predicting thunderstorms because the thunder parameter or the CAPE parameter was unstable for much of the time. In fact, I think if you go to Florida, you'll find the lifted index is almost always negative. And so what we're trying to do is say, well, can we narrow that? Because if you're interested in the lightning forecast and what's the real area of risk, you don't like to overwarn people. And our feeling was if you just use CAPE alone, you're overwarning. And then we said, you know what might be the best thing is to combine the two. That is, look at combining the attributes of the environment and the attributes of the cloud physics itself for perhaps the best answer to get at a lightning forecast.
Mm-hmm. Yeah, that makes total sense. Thanks.
Yeah, I should say I'm not a modeler per se. We took a brief look at it to see, you know, what can we come up with that might be useful. And clearly there's room for more research and study of this type of thing, which I know you've also looked at.
Oh, yeah, I forgot to ask, because I missed maybe 15 minutes of your talk in the beginning. Was this effort kind of like making the data records of lightning?
Yeah, this is on the path to making the climate data records for the essential climate variable. So, you know, the GLM data only goes back to when we launched, so that's early 2017. UMetSat just launched, and so their data is not first available to the end of this year. The ground-based data sets in varying years can go as far back as 2004, won't be as good then because they've all expanded their networks. I would say the key takeaway is the satellite lightning observations are going to continue into the 2050s. So really, we're just getting started, but the lightning time series will continue for the next few decades. So it won't be me, and I guess it won't be you either, but maybe our students and grand students or whatever it is, you know, will have these data sets available to do some groundbreaking research.
Yeah, very exciting. Thanks.
Yeah, by the way, the talk is supposed to be recorded, so you can catch that first 15 minutes later.
Mm-hmm.
It is recorded, yeah, and it'll be posted on the ASIC YouTube channel, which is ASIC UMD, by the end of the week. So if anyone has any other questions, you can go ahead and ask them. Go ahead, Louis.
How you doing, Steve? So Louis.
Hey, Louis.
Yeah. Hey, listen, first of all, with respect to David Bright, he had other parameters besides the CAPE that would, you know, you got to release the instability. So you got to have something mechanical there that, you know, so it was just the background state. Anyway, I was curious about the global coverage. You know, we were, I think it was 2019 satellite conference where it's pretty obvious, you know, the US was falling behind in terms of its global coverage of the geostationary satellites. And obviously with GeoXO, it's, you know, that's a major effort to reestablish, moving into the next generation satellites. But when I left the Weather Service now over a year ago, the Himawari, the Japanese and the Korean satellites were becoming increasingly used by the Weather Service within the Pacific. And I don't recall whether they had plans for a lightning mapper or not. So in terms of the total coverage that let's say the Weather Service here is going to be accessing, is that a problem? Or has that been is that being dealt with, I guess?
Yeah, I'll give you the backstory. And by the way, I'll see you in Wisconsin for our 75th anniversary of
Yeah.
the department.
Yep, yeah, looking forward to it.
So, for the last round, KMA Korea and JMA Japan were looking at what instruments they wanted, and due to cost, they decided not to fly Lightning Mapper, but they looked at it because WMO and the Oscar database that they have, the observing system database, currently encourages in their Vision 2040 that we should ring the planet with Lightning Mappers is one of the measurements, including sounders and a whole host of things. And because of cost, they didn't go there. So now Japan also studied it for their next Himawari 1011. And actually one of our postdocs was involved with that study for them on whether they would have a Lightning Mapper. And again, they wanted the sounder more than they wanted the Lightning Mapper. So they're going to have an imager and a sounder. And they have some coverage of Japan with lightning networks on the ground, but they don't have coverage of the storms that are coming towards Japan. And so that was their primary interest. So yeah, they both looked at it, but they decided now they would go with the multispectral imager and the sounder. Now, interestingly, India has come back again. They one time looked at having a Lightning Mapper on their satellite, and I think they're still thinking about it. They haven't made a decision. And then I was at the WMO Second Climate Observing Conference, and a representative of the Bureau of Meteorology was there. And she told me they were doing a study about maybe Australia Space Agency could fly a Lightning Mapper, or maybe build one and provide it for Himawari to fly on the Japanese satellite. I've not heard any more from them. And the question the users were asking is a similar one that we got asked here in the US is, okay, I got a ground-based network. Why do I need a satellite? And so, yeah, you can see where the lightning struck the ground, but you don't get any of the earlier indication or the propagation information the satellite could provide. And she was going to go back to their fire community, and I've not actually touched base with her since then. And Brazil, a long time ago, had looked at a Lightning Mapper as something they might fly. So they all talk about it, but you know, those with the deeper pockets, I guess, are the ones who are able to do it. Maybe, you know, in the next version, they'll do it again. So we'll see. But anyway,
Okay.
Thanks for the question. Good to hear from you.
Yep. Take care.
Do
Yep.
we have any last questions before we want to wrap up today? Okay, well, thanks everybody so much for coming. Thank you to Dr. Goodman for giving us this great talk today. As I said earlier, the recording will be up on our YouTube channel before the end of the week. That's linked in, I believe, John's emails, but if you can't find it, just email me. And thanks, everybody. Our seminar series will continue next week.
All right. Thank you all.